Right, in the first video we talked about the chain rule and the general power rule, and now we're going to go ahead and talk about how we can simplify the derivatives of functions using algebra. And I have three perfect examples to show each steps of algebra to simplify derivatives. All right, the first algebra technique that we're going to learn today is simplifying by factoring out the least powers. So here we go. We have the example x squared times radical 1 minus x squared. All right, let's go ahead and just write the original function first. Now we're going to convert the radical term into a quantity power term, because radical means you're taking the 1/2 power of the inner part. So here we go. We write that as x squared times 1 minus x squared to the power of 1/2. Now we have the product of two functions. Why don't we use the product rule? In fact, the product rule states that we're going to take the derivative of this function first times the second function, plus keep the first and take the derivative of the second function. And if you do that, let's see what we get. And this is in fact written explicitly. So the first function times the derivative of the second function. You can always change the order, by the way, and keep the second function and take the derivative of the first function. Again, since this is a sum, you can always change the order of the summation here. All right, so we're going to take care of individual derivatives here. To take care of this derivative here, we're going to use the chain rule or the generalized power rule or the general power rule. And for this one, we already know the standard power rule to take care of it. Let's apply the generalized power rule here. So we're going to put 1/2 down and keep the inner part as is. Subtract 1 from the exponent, so it becomes negative 1/2. And then we're going to multiply everything by the derivative of the inner part. So 1 has a derivative 0, and negative x squared has a derivative negative 2x. So this is just us taking care of the first derivative here. And the derivative of x squared here is simply 2x. Here we go. We have everything written in the cleaner form. And let's see what we're going to use next. Now we're going to try to simplify as much as we can in regards to constants here. So if we have 2 here, we have another 2 here. Those are divided out, and we're going to rewrite this expression. Also notice that we have an x term as a multiple, and you have another x squared term. So x times x squared is going to be x cubed. Here we go, negative sign out. We have negative x cubed, 1 minus x squared to the power of negative 1/2. And we had 2x here, 2x comes first, and 1 minus x squared to the power of 1/2. Now we're going to use the factoring out the least powers algebra simplification here. And look at those terms here, 1 minus x squared to the power of negative 1/2 and 1 minus x squared to the power of 1/2. The coming with the least power is this term because it comes with the power negative 1/2. So in the next step, we're going to try to factor that out. And notice that there's another common factor here because we have 2x here and x cubed here. So x comes with power 1. So the least powered term for the like terms x cubed and 2x is 2x. So we're just going to factor out x together with this term here. So let's do it. Here we go, x 1 minus x squared to the power of negative 1/2 is factored out. So what I'm left here is just negative x squared times 1. And from here, I have only 2 times 1 minus x squared, because this term here multiplied by that is going to give us the power 1/2, because this comes with power 1. So after factoring out, we're going to simplify the inner part of the brackets. And in fact, we have negative x squared plus 2, negative 2x squared. So the inner part of the bracket is going to be simplified as negative 3x squared plus 2. And the final form of the derivative of the function is coming with a very compact form. In fact, it's given as like a quotient. And this is probably the simplest form you can go with for f prime. So factoring out the least powers is a very common technique in finding the derivatives of functions. So we're going to even use this type of simplification in the next example. So this time we have a quotient, and we're going to try to simplify the derivative of a quotient. All right, so we have x over cubic root of x squared plus 4. So we write the original function. And now root terms are converted to the power terms. So we have cubic root of x squared plus 4. We're going to rewrite that as x squared plus 4 to the power of 1/3, because when we take the derivative of that piece, we're going to be able to use the power rule for differentiation. In fact, the general power rule for differentiation. All right, here's what we have. So now we have the quotient of two functions. Why don't we use the quotient rule to come up with the derivative of this quotient? In fact, the derivative of the quotient is top prime times bottom minus top times bottom prime, all divided by bottom squared. I'm going to write this in details in the next slide. Here we go. The derivative of the top is 1, so 1 times the bottom, plus keep the top and take the derivative of the bottom, but the derivative of the bottom follows the general power rule. In fact, we put 1/3 down and subtract 1 from the power and multiply this by the derivative of the inner part, which is simply 2x. And that's exactly what we have here for the derivative of the bottom. And here we have the bottom squared, so it comes with the bottom comes with the power 1/3. If you square that term, you're going to have the exponent 2/3. Right now we're going to try to simplify the whole quotient, and we're going to use the factoring out technique again. So we have this term here, x squared plus 4 to the power of 1/3, and you have x squared plus 4 to the power of 2/3, and the one coming with the least power is this one. So why don't we factor this out together? Here we go. So this is x squared plus 4 to the power of negative 2/3. And what we have here is, so now we have the x squared plus 4 to the power of 1/3. So to be able to make it happen, I have to multiply this by x squared plus 4. And we have the leftover terms here, 2x and x times 1/3. So we have 2/3 x squared. Let's simplify this further. So we have x squared plus 4 to the power of negative 2/3, and I have 1/3 x squared plus 4. And in fact, I can even simplify this further by finding a common denominator. Okay, so this becomes in fact x squared plus 12/3. So in the next step, we're going to see that I'm writing this whole thing in a more compact form. And we also had this part out, and we have the denominator here. So now we're going to have a negative reciprocal, so negative power, so we're going to write it as a reciprocal. So it's 1/x squared plus 4 quantity power of 2/3. That makes the bottom coming with the power 4/3. And this is the last or final representation of the derivative of f. All right, let's go with this final example to finish this video. We have a quotient raised to the power of 2. What we're going to do is to use the generalized power rule first. You have the inner part here, and that inner part is raised to the power of 2, and the derivative of that is you put the power down, you subtract 1 from the power, so it becomes to the power of 1, inner part raised to the power of 1, and you take the derivative of the inner part. But the inner part is a quotient, so we're going to use the quotient rule to take care of this derivative in the next step. Here we go, the quotient rule applied here. So we take the derivative of the top, which is 3, times the bottom, x squared plus 3, and we keep the first, we put the minus sign, don't forget the minus sign here. We keep the first and take the derivative of the bottom, which is 2x, and we take the square of the bottom. From this moment on, the rest is just simplifying at the top and rearranging the terms. Here we go, we expanded this part here, so 3x squared plus 9. All right, here we go. And then we have minus 3x minus 1, 2x, and that is simplified as minus 6x squared plus 2x. In fact, you expand this out. And just bring the like terms together so that this term is simplified to this quadratic. All right, this is the final form of the derivative, and here is your y prime. All right. All right, algebra is very important in simplifying the derivatives. So this finishes this video, and please watch my next video to see what I'm going to say about how we can find the derivatives of transcendental functions and natural log functions using the chain rule. All right, bye.